Good morning, Precalc. Today we're going to be working on 8.2.5, answering the question, how many rabbits are there, which is about the Fibonacci sequence. So with Fibonacci sequence, it's this sort of idea of this sequence that's found in nature, often called the golden spiral, where the idea is it sort of started from this guy named Leonardo of Pisa. And he sort of had this idea of talking about this situation where you start off with a pair of baby rabbits. It takes a month, 2 months for the rabbits to mature. And then the idea is like you're eventually each month, the adult rabbits will continue to produce baby rabbits. And so with this, we sort of have a table, in each that we have here that we're going to sort of fill out sort of to recreate the Fibonacci sequence. So to start off here, one of the things we have is we're talking about pairs of rabbits, and not just individual rabbits. So we're not just having rabbits suddenly mitosis and split into a baby rabbit from a parent rabbit. These are talking pairs of rabbits. So we're calculating pairs of rabbits, which is what it means when it says total rabbits. So with this, we're going to just sort of start off with adding up each row. So if we do that, we have 1 here, 2 zeros, so we have a total of 1 pair of rabbits. And then we're going to do the same thing down here. We add it up, we only have 1. Oop. Let me zoom in a little, just so then I can write a little bit tighter. So we have 1, and then over here, our rabbits sort of reached maturity and they created some babies. So now we have 2 pairs of rabbits. Well, in this next month, the parent rabbits are going to make another pair, so now we're going to have 1 here, 1 here, and 1 here. So now we have 3 pairs of rabbits. Well, the next month, these teen rabbits sort of mature, so now we have 2. These baby rabbits sort of mature into teen rabbits, so we have 1 here, and then these 2 pairs of adult parent rabbits will produce new baby rabbits. So if we add that up, we now have 5 rabbits, 5 pairs of rabbits. So same thing again, this teen rabbit's going to become an adult, so now we have 3 parents, 2 teens, and we are also going to have 3 bebés. So we add this all together, 3 plus 2 plus 3 is 8. And then the next thing happens, we have these 2 mature, so now we have 5 parent rabbits, 3 teen rabbits, and now 5 bébé rabbits. And we add it all up, we have 5 plus 3 is 8, plus 5 is 13. And we do it again, 8, 5, and then 8. So 8 bebés, 5 teens, and 8 parents. So we add this all together and we end up with 21 rabbits. Now we'll have 13 here, 8 here, and 13 here. So we now have a total of 34 rabbits. We do it again, and we have 21, 13, and 21. For a total of 55. Once more we do it, so we get 34, 21, 34, and so then we end up with a total of 89, and then we have 55, and 34 for a total of 144. Now, as you sort of look at this sequence, you can notice that it is a sum of basically the way it works is we're just adding the previous term with the current term. We start with 1s and we add them together. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, so on and so forth. Now, with this, we're going to have some questions to answer. And one of the things we're going to look at is the idea of applying limits to this recursive series and sort of seeing, like, is there a ratio that it eventually approaches? So if we look at that, one of the things we're going to do, this is sort of the idea of, we just sort of went through filling out the table, which in part answers 132 part A. But we're also going to sort of look at part B. So if we wanted to write this as a recursive series, the way recursive series works is basically you have your sort of a future term. So if you say like our first term, our first sort of, or not a zeroth term. Sorry, they call it our first term. I usually like to start with the zeroth term, but we're not going to do that. So our first term is 1. Our second term is also 1. And it wants us to sort of make an idea of what is a sub n plus 2. So if we think about, if we plug in 1, or we plug in 1 for n, so if we think about it, a sub 3, which is 2, is equal to a sub 1 plus a sub 2. So if we think about sort of turning it into an n term, that would be if we plug in 1 for n. So what we can think of it is, if we plug in 1 for n, then we have over here a sub n plus, because the 1 is n. And if we think about it, this 2 would actually be a sub n plus 1. Now, with this, one of the things we're going to sort of look at is we're going to sort of compute some ratios of terms, which we're going to do in 133. So in 133, we're computing some ratios of terms. Because, why not? Maybe these things approach something interesting. So what we're going to do is ratio of the top term over the bottom. The next term over the previous term. So a sub 2 over a sub 1. So if we write it out, we have 1 over 1. And then we have 2 over 1. And then we have, let's see, it would be 3 over 2. And then next would be 5 over 3. And then it would be 8 over 5. And then finally 13 over 8, 21 over 13, 34 over 21, which I should probably move that one so y'all can see it. So let's move these two so we have them down here. 34 over 21, and then the next one, next set would be 55 over 34, and then 89 over 55, and finally 144 over 89. Now, if we look at this, number, it sort of seems like it might be approaching a specific number. Because we had it go from, like, over here we had to go to 1, and then it went to 2, and then it went down from 2 to 1.5, and then 1.66, and then 1.6, and then up again. It seems to sort of be varying slightly. It's sort of like doing a little wave thing, but it does seem to be approaching a specific value because now it's sort of oscillating between, because we had, in terms of the range of our values, we started at lowest number we had is 1, highest number is 2, and now it's sort of narrowing in between that. So in my mind, because it sort of keeps narrowing in onto a smaller and smaller range between each term, then it's, to me, seems like there's probably going to be a limit. Now, if we want to estimate that limit, it's a little bit like, when we think about it, it's a little bit of a challenge. So we might have to rearrange how we write this function to sort of estimate that limit. So what we're going to do is sort of dissect the idea of what type of things we have here. So if we think about labeling each of these sections as a certain term, so we'll go ahead and do that. We'll call this A sub 1, A sub 2, A sub 3, A sub 4, and so on and so forth. Now, what I'm going to do is, if we look at each of these, we have, for everything except for the first one, it looks like we have a 1 added into each of these. So what I'll do is I'll split up A sub 2. So if we think about it, 2 over 1, that would be 1 plus 1. And then for A sub 3, we look at it. Well, we factor out a 1, we're left with 1/2. So we end up with 1/2 plus 1. And then for number 4, we take out a 1, we have 2/3 plus 1. And for the 5th one, we factor out 5 from here, we have 3/5 plus 1. So if we think about it, if we look at our terms, we have A sub 3 is 3/2, and then we have 2/2 over here. A sub 2 is 2, and we have 1 over here. So if we look at it, if we sort of look at sort of the idea of recursive definition, I have a feeling that we could sort of define our definition as 1 over A sub n plus 1, so the next term in the sequence, is equal to 1 over the current term, or the term we chose, plus 1. Because it sort of applies, because if we think of this 2, this is the same value as A sub 2. So we have 1 over 2. And then we have A sub 3 over here as 3/2. If we flip that over, we have 2/3. So in my mind, this is a pretty accurate way for us to find the answer, or to find a value. So when we do this, we end up with, if we think about it, that it's sort of approaching something, we could take the limit of it. And so if we do take the limit of it, A sub n plus 1 equals 1 over A sub n plus 1. If we take the limit as n approaches infinity, eventually, like infinity plus 1 doesn't really mean all that much. So if we take the full limit of it, then what we end up with is something which sort of approaches, you have the idea, we'll just say A sub, we'll do a little substitution, A sub n equals x. So we end up with something that sort of approaches x equals 1 over x plus 1. Now when we do that, we can then sort of multiply both sides by x. And so when we do that, we get, I'll do this in green, x squared equals 1 plus x. When we do some subtraction, x squared minus x minus 1 equals 0. And from here we can use the quadratic equation. So it would be x equals negative b, so that would be negative 1 plus or minus the square root of b squared, so that would be negative 1 squared, minus 4ac, which is 1, and negative 1. Let me undo that weird circle. And then all over 2a, which would just be 2 times 1. And I cut it off a little bit, so bam. And then we end up with x equals, which I'm going to just close Chrome window for right now. X equals 1 plus or minus the square root of 1 plus 8, or plus 4 I should say, because I can math, all over 2, which equals 1 plus or minus the square root of 5 over 2. So I would say what we can probably do is we can ignore the minus because root 5 is greater than 1. So if we had that, we'd have a negative number, which doesn't make sense for a Fibonacci sequence. So what we have is the limit of, as a sub of n approaches infinity, of a sub n equals 1 plus the square root of 5 over 2. And that's sort of the limit of the ratio that we get for our Fibonacci sequence. So like the ratio between terms ends up becoming something like this, which is, when mathematically we do it, is about, so when we calculate it, we get about 1.61 as our sort of value here. And this is sort of an important value because this is what's called the golden ratio. And it is found everywhere in nature, and sort of this ratio between all of our different terms that we have in mathematics, or not in mathematics, but in the Fibonacci sequence. So like as you get closer and closer to infinity, as you go further and further along the path, you basically could end up with a geometric series using this recursive series where you have a ratio between terms of 1.618. And that would be the constant ratio, and you would get a pretty accurate assessment or a pretty accurate value for future sections, for future values of your Fibonacci sequence. So if like you chose an n value of say 1,000, you could actually just do 1.618 to the 1,000, and you'd get a pretty accurate idea of how many rabbits you would have after 1,000 months. Of course, the ratio gets a little bit better the more digits you have, as well as the bigger the n is, because it is, once again, the limit as n approaches infinity. But it can be a fun way to sort of approximate values of the Fibonacci sequence directly by sort of converting it into a geometric series. So as for what we have to do for assignments, you're basically doing, so we did most of 1-131, which was filling out this table, and 1-32, and in fact 1-33. You're going to do 1-34, where you're just actually reversing the ratio. So you're doing the current term divided by the next term, and you're going to sort of see what that might approach as a limit. And sort of, if you think about it, mathematically, it might be appropriate to call it the reciprocal of this, which would make the most sense, because if you think about it, this is what it equals in the other one, and this new one is just a flip over of it, so it's doing the current term divided by the next term, so that would be just 1 over this limit. And then you're going to sort of do a little bit more work with some recursive functions, 8-1386, 136, below, 137 and 138, and you're just going to be completing those where you're just looking at ideas of recursive definitions of series. So the idea is that you have your value for your next term, you're calculating it using your current value, and then your further one. So if you do, you're going to basically compute the first 5 terms. So for your n, you're going to put 1 here. So x sub 2 would be 1 times 1 minus 5 plus 5, and so on and so forth. And then you're going to do the same thing for x sub 1 equals 2 and plug it in and write the first 5 terms. And then what you're going to do is, for 37, you're going to figure out all the terms, all the starting terms that can happen where this ends up being the same value. N sub n, x sub n plus 1 equals x sub n, is the idea that you're going to try and solve. Which you might do very similarly to how we did it over here to solve for the golden ratio. So that's the idea there, and then you're looking at 3 different series in 38. So, longer than normal video, and I apologize for that, but I hope this was helpful, and have a good day.